First of all, I'll start off with the obvious. I may look a little bit different than I did in the PR shot, but I'm doing fine. I just had a little bit of surgery around my eye, so I have that covered up and patched up still. I was playing over the weekend with our new cloud avatar engine and thinking maybe I should just go through and present as an avatar. But I know, I think it's much better being live in person for now as we're perfecting the avatar technology. So really excited to be here talking about the metaverse.
Well, we hope you have a speedy recovery. The thing that we're talking about that's really interesting is around computing and sustainability. And it's not sustainability in the way we've been talking about it in terms of environmental sustainability, but it is around energy. And I'm just fascinated because I'd never really considered it. So where I'd like to start is you talk about the computing power to build AI factories and digital twins. We've talked about digital twins on the show before, but I'm not sure what an AI factory is.
When people think of the metaverse, I think that the first thoughts go to maybe social networking and VR or AR. But of course, any enterprise that moves atoms, physically moves atoms, right? They manufacture something. They need to start thinking or are thinking about how do I create a digital twin? And a digital twin is not just a photographic simulation of it, but of course, a digital twin has to, of a real atom, of things made of atoms, have to follow the laws of physics. So that means they need to be simulated. And simulation these days is not just about simulating the laws of physics, but applying AI in shortcuts. And an AI factory is our sort of term that we used to apply to the way you develop AI software, which is really different than the way that you develop a traditional software.
That was a question I had saved for later, but let's go there right now. My background, our audience knows, is in visualization software with Wavefront here in Santa Barbara. And I don't ever remember being in a conversation where someone said, how energy efficient is our software? What does that mean?
Well, let's put that back in the AI factory context. In a real factory, you're taking in raw materials, you're applying energy, electrical energy, human energy, tool energy, and you're transforming that raw material into some finished good. And an AI factory is, of course, not a room full of computer scientists typing away code that you might normally think of. There are, of course, computer scientists involved, but they're taking in data, real data from the real world, simulated data sometimes, and they feed that data into a computer program, an AI framework, using some sort of a pre-built model as a starting point. And out the other end comes an AI program, which is then run right in the steps of inference. So the AI factory is that process by which you create the AI programs. Now, it just so turns out that it requires a tremendous amount of computational power. The concepts, the algorithms behind modern day AI, the deep neural network, go back 30 or 40 years. You never had enough computational power to do it. So it's increasingly important as you apply that computational power, can't just be with brute force. It has to be done intelligently in an efficient way.
When you say 30, 40 years ago, that was when we founded Wavefront. And the supercomputer at the time was a Cray. And that was huge and the fastest thing on the planet. And I've been paying attention to the kind of work you folks are doing. How much faster is compute power now compared to that Cray 40 years ago?
Well, everyone wants to go through, and we've been taught through generations of PC advertisements, first in the newspaper and then online, about megahertz or gigahertz, gigabytes of RAM. And all of those factors were important when Moore's law still stood, which in effect meant that You could every 18 months or 24 months, you would pay the same amount and you would get double the compute power, typically by getting a transistor that was double the speed. And of course, that's ended. That started to end about 10 years ago. And a new type of computing needed to be developed
Mm,
in order to use all of the new transistors that you continue to get. Our largest chips today that are being built by TSMC or Samsung or Intel are approaching 100 billion transistors, right? But they don't run at 100 gigahertz or 100 million gigahertz. So a new type of computing, we call it accelerated computing, and that's a term that's generally being adopted in the industry. And many people, since Wavefront was invented, you had a big Cray supercomputer, was a big room-sized supercomputer, and then we saw cloud computing emerge. And of course, everyone is seeing pictures of these massive cloud data centers
yeah.
filled with hundreds of thousands of CPUs sometimes, and spanning football field after football field. And with accelerated computing, it turns out the computing is so powerful, it can be put together much more closely. And the new supercomputers we have today are more like the size of perhaps a basketball court versus football field.
No, no, okay. So first off, no kidding. I didn't realize that. That you had to figure out how to get the form factor smaller to get the speed. So and I love this when I remember everybody when I said he's in the room where it happens. You're one of the principal architects for like figuring out how to do this. So one of the things you were talking about was how much energy it takes. So as those football fields got bigger and bigger, and now that's over, and now we can do things much smaller. Have we been able, and I guess the answer is yes. I don't want to lead the witness too much, but have you figured out how to do that energy efficiently?
Well, we're getting there. At the hardware level, right? One of the things is if you think back to when you were at SGI, I was at Sun Microsystems, and I remember Greg Papadopoulos was our
Oh,
CTO, and he said eventually flops will be free. We won't talk about the cost of a chip and how many flops it'll be. And he said, well, what you'll care about is data movement and the
yeah.
cost to move bits. And if you think about in running an AI supercomputer today, that cost of moving the data around, which is directly relative to how far away it is the biggest cost, costs much more than the actual computation. So again, that's why NVIDIA is becoming a huge networking company. And again, so much of our work today on building a supercomputer is not just on the processors, but on the networking to bring together all those processors. That's one part of it. The second part of it is, of course, software. Supercomputing is a data center scale problem. You can't just make a chip faster and expect it's going to run GPT-3 twice as fast because the chip is twice as fast. You need to think of all those layers in the software stack between the GPT-3 model, TensorFlow or PyTorch underneath that, the operating system, the libraries, the networking software. We're putting together thousands, tens of thousands of processors in one supercomputer that all have to work together. The coordination of bringing that all together at the software level can only be done if you look at that problem of building the AI factory, the supercomputer, at the data center scale, like supercomputers were built.
You've helped me understand. Hopefully, the audiences will understand the AI factory part of this, because as soon as you mentioned a whole lot of words that I'm not familiar with, but that's part of what's happened is the complexity has gotten orders of magnitude more complex to be able to solve these huge problems. So let's go to the why we need these bigger, faster computers. Talk about some of the huge problems that can only now be solved with these kinds of computers.
Well, some of the huge problems that can be solved today and couldn't be solved just a few years ago actually lead on to even huger problems.
Hmm.
One particular digital twin that we're working on is we call it Earth 2.
Hmm.
It's a digital twin of Earth. We're super excited about that. It's going to be a very long-term project, but already we're making a number of different steps forward with that. And happy to talk about some of those.
So I've been privy to, just because I pay attention to what you're working on. Earth 2, when just to remind everybody, a digital twin is literally a twin of something that exists in the physical world, and everything, to your point, is not just what it looks like and how it behaves and how it recreates the actual physics. So it is a digital twin, and in fact, that can be done on a lot of different levels in robotics. Those kinds of things, it's pretty easy to understand how to do that. But when we get into digital twins of physical systems, the complexity gets it just gets orders of magnitude more. For instance, digital Earth is going to have climate and clouds and things like that. Tell us about how that complexity changes things.
Yeah, so today we're working on just some of the early models of Earth 2 and some of the early types of digital twins. And so we, to start with, are working on climate modeling. Now, of course, there are large weather forecasting centers around the world, climate forecasting, and we're working with many of them. One of them, in the particular model we've started with, comes from the European Center for Mid-Range Weather Forecasting, and it's called ERA5. It's the fifth iteration of the ECMWF, initials for that model. And what this does is it models the atmosphere of the Earth, right? And the model goes through and goes all the way back to 1950 to today. This is the fifth generation. Every few years, they do a new model. And using the largest supercomputers in the world, it's able to go through over some weeks of processing and be able to simulate the climate at a 25-kilometer range. And you say, well, that's pretty good. 25 kilometers is one end of Santa Barbara to the other and out a little bit. If I know if it's raining 25 kilometers away, it's probably going to rain here. But it turns out in climate modeling, that's not good enough, right? Because you need to figure out, based on what happens today, what's going to happen 20 years from now.
Mm.
So we applied some of so now these climate models have always worked on simulating, right, writing a computer program that understands the laws of physics and runs, in effect, the laws of physics. And that's why it can do it down to a certain level, this 25-kilometer range model, because as you make the physics smaller, of course, it's a kilometer squared increase in the amount of performance. So the first thing that we did is we pioneered, there's been work in technology. If you think about it, if you can train an AI program to recognize cats and dogs or red lights versus green lights, why can't you train an AI model to understand the laws of physics?
Mm-hmm.
And that's what we've started to do. NVIDIA has a program called Modulus, which we applied to that climate model in going through in simulating the climate. And so instead of calculating the laws of physics at every point along that climate model, we use AI to, in effect, guess, shortcut, and only calculate the laws of physics when we had to. Simply by doing that, a simple change in replacing some of the physics simulation with an AI simulation, we were able to speed up the ERA5 model by 25 times. So think about that. That's the equivalent of getting us from 25-kilometer resolution to 1-kilometer resolution. So a great step forward, though not enough.
When you talk about that 25-kilometer and people can think about when we were watching the hurricane, and they were looking at the models, and they said the US model shows it going here and the European model, and you would see all those colored lines. Those are the models you're talking about. Is that correct?
Exactly, right.
Got
And
it.
we had, unfortunately, that was an older hurricane that you're referring to. But just a couple of weeks ago, we had a terrible
Yeah.
hurricane in Florida. And in fact, one of the problems was the earlier models from the day before were showing it being about 25
Exactly.
miles north,
That was,
in
there you go.
missing
Yep.
Fort Myers. Of course, what happened is instead of landing 25 miles north of Fort Myers, it hit directly center in the city. We had some employees in the area. Luckily, we were able to get out safe, but not everyone was. And so that's the real impact of how this work that we're doing in being able to improve climate modeling. Now, unfortunately, we're only part of the way there. We're at 1 kilometer level today, roughly, using AI. We're not doing it at a time scale or quick enough. Again, it's still, to do a 1 kilometer model, even with AI, is still taking many weeks, way too long for to help the Hurricane Ian victims, right? But to get even farther right along is you need to get to 100-meter resolution. At 100-meter resolution, you're able to resolve the physics of storms. And actually, to get to the most accurate sort of long-term models, researchers want to get to 1-meter
No
resolution,
kidding.
right? So from 1 kilometer to 1 meter and decrease that time scale. So we're looking literally at million X increases in performance are needed before we can really realize that vision of Earth 2.
I think that our audience, like me, is just the scale of what you're talking about. The scale of the problem is immense. I have one last question around the sustainable. I have a lot more questions, but one that hit me as I was doing some research. Real quick answer: we've heard that there's a lot of energy used in Bitcoin mining. And I don't think people who pay attention really knows that. Could you couple of sentences on what does that mean?
Well, Bitcoin is a cryptocurrency. Most of the Bitcoin mining today is being doing with very simple specialized ASICs. But again, there's a lot of work. Again, when we talked about software, AI software, other types of software being used to make computing, AI computing more efficient. In the cryptocurrency world, people are doing the same thing. They're looking at how do we create new algorithms that don't require as much compute power to create that cryptocurrency.
Marc, thank you so much for helping us understand these really complex issues. There's, like I said, I've got thousands of questions. Thank you.
Thank you.